Hey guys, this is Srini and you're watching Python tutorial videos on my YouTube channel Python for Microscopists. In today's tutorial, I'm going to talk about Fourier Transform and how it can be relevant for image processing. Now, Fourier transform is a mathematics topic, I should say. It involves equations. If you really want to get your hands dirty, and in fact, if you have engineering background, there is no excuse. You should know, or you should have known what Fourier transform is. And if you come from life sciences, I'm not sure. Depending on the curriculum, you may or may not have been exposed to these type of Fourier transforms in Taylor series, in the Fourier series, and so on. So but don't get intimidated. I'm going to keep this at a very high level. If you want, you can always find other videos on YouTube that go into a very in-depth discussion about Fourier transform. So as usual, let me jump on to the drawing board so I can explain things, hopefully with minimal math. Now, I enjoy cooking, so let me use cooking analogy for Fourier transform. For example, well, I primarily cook Indian and Asian type of food. So let's just take one or one dish. Like for example, let's say you are trying to cook palak paneer. Okay, in Indian, that's nothing but cheese plus spinach. So from the name, you know that okay, to do this, to cook this, you need spinach. You need some sort of I mean, paneer cheese, and in addition to that, of course, it's Indian food. No Indian food is complete without onions, and you need some tomatoes, and you need a whole bunch of spices, right? So these are the ingredients. Now, how do you know what the ingredients are? Well, you go up and look at the ingredients. Yeah. But think of Fourier transform as something that deconstructs. So if you have a dish, it actually deconstructs the dish and it tells you exactly what the components are made up of. Okay. Uh, so hopefully that's a good analogy. If not, let me actually switch to the real life scenario where, okay, so if you have, for example, if you are listening to music, right? Music is nothing but a bunch of sound waves. Yeah. So it's actually the speaker, yeah, some sort of a voltage is applied to the speaker. So the speaker actually vibrates, which moves the air. So it's nothing but okay. Let's say you just started the let's say the audio, and then you actually okay. So here is how the wave looks like, and the sound waves I mean looks like, and then okay, you may have something like this, and then you have again I'm this is very slow moving, as you can see. Now this is how your sound wave looks like, but according to Fourier, every wave, can be decomposed into a bunch of other waves. For example, so here, this wave can be represented as a sum of multiple waves. Again, I'll try to do a good job. So this can be a sine wave, okay? So if you have a sine wave like this, so this wave is nothing but a combination of this plus maybe another wave, let's say it starts right here, so they both add up to this. So a combination of these two waves, okay, and this can be like this. Again, I'm not accurate here, as you can see. Maybe I am. Yeah, when you add these two signals, the red and the green, you should get the blue. Okay, hopefully you got the point. So in a way, this signal that is coming out of this speaker is nothing but a combination of a sine wave that has specific frequency and phase, and also it's a combination of another wave that has another frequency. Okay, in reality, the signals obviously are a bit more complex, so you may have like a, I don't know, another wave that is have much better frequency, much faster frequency, and so on. When you add all of these, then you get a final signal that actually is a reconstructed signal of what you're, yeah, listening from the speaker. Okay, this is again using the sound wave analogy, but I hope it makes sense to you guys. Okay, it's nothing but uh, any signal is a summation of individual sine waves or cos waves. They both are very pretty much the same, right? So summation of these. Now, what Fourier transform actually does is it actually gives us the result of, okay, this is your input, so here are the dominant frequencies that actually are dominant waves that actually add up to give us this specific signal. Okay, and we're going to use that for image processing, and I'll do that in the next tutorial, but let me actually uh, I was hesitating here to actually write an equation, but why not? Yeah. So let's say, okay, what is the Fourier transformation from an equation point of view? Let's say this is my Fourier transformation is, it goes from minus infinity to plus infinity. Okay. And then your signal in the time frame. Okay. Again, the Fourier transform, all it's doing is taking something that is in the time domain and then converting that into some signals in the frequency domain. Okay, if you only have one sine wave that has specific frequency, then the Fourier transform of that sine wave is nothing but let's like one little data point at whatever that frequency is. Okay, that's it. If you have another sine wave with a different frequency, then that would be over here. If you have a combination of these two, then you have like these two present over here. So Fourier transform again is decomposing your signal into individual sine waves, but then each sine wave can be defined by a frequency and phase, right? So that's what it is converting this to. Okay, so this is your initial signal in the time domain or spatial domain, if you want to think about it. And e to the power of minus j, again, don't get intimidated. I'm going to get into the code in a second so you see how it is easy it is to verify any of these. So e2 minus j 2 pi, let's just say frequency t and as delta t, okay, dt. So now in reality, your signal is not going from minus infinity to infinity, right? In reality, when you start collecting your data, you start collecting it at a specific time period. So when do you start collecting your data? At a time equals to 0 or at some point. So, and also in reality, you're not collecting continuous data, right? So when you actually collect your data, whether it is sampling, whether it is pixels in your image or sampling sound, in fact, it is discrete data points when you are actually collecting them. You're not actually collecting them in a continuous way. That means integration is not the one that we need. It's actually a summation, which makes it from a Fourier transform to discrete Fourier transform. Okay, so this is what makes it discrete. And my n equals to 0, we start at some point all the way to some number over there. And again, same thing. So let's say I could have used time here, but number of let's use n, and then again e to the negative j 2 pi, okay, k n over, because we have n samples right there. Okay, I believe there is a 1 over n term here also, but let's not get into technicalities over there. Okay, uh, so now this term, I mean, this is nothing but think of this as your input signal, which can be your wave, or which can be our pixels in the image. And this is what it's actually complex coefficient. And this j right there, by the way, it's this makes this a complex number, right? So this is a complex. Again, if you uh, go back to your seventh grade, eighth grade, whenever they cover this topic in your high school, they are real numbers, they're complex numbers, right? Which is nothing but 1 plus, I don't know, 5j, right? This is a complex number. So this is a complex coefficient right there. Okay. Now, so this is, I think this background should probably do before jumping into the code and explaining exactly the same thing, but in the code form. So let's jump into our Spider IDE. Okay. Now let me copy and paste a few lines of code that actually converts, that actually generates a sine wave, except in 2 dimensions. Okay. So in fact, let me plt.imshow. Let's actually show my image. So I'll share this code with you, but here, this is nothing but a sine wave, except instead of looking at 1 dimensions, instead of looking at, instead of looking at this as, 1 dimension sine wave, we are actually doing 2 dimension, which means we are actually bright spot here, okay, dark bar, bright here, dark there, and so on. Okay, so if I go back, the bright, the peaks and the valleys, peaks and the valleys. Okay, so this makes it easy for us to understand this because again we are thinking from an image point of view. Okay, so again, I don't want to get into this code. Well, maybe a little bit. If I actually change this to a value of 60, for example, then you'll see that where is my plt.imshow? And let's look at the image. So I'm just changing the frequency here by changing the value. So by going a higher value, because we are dividing this here, I'm actually decreasing the frequency over there. Okay, by changing the value to, for example, 3 here, now the frequency should go up. Okay, should be pretty high over there. So, and we'll see the effect of changing the frequency on our Fourier transform in a minute. Okay, so let's go back to, I don't know, a value of 60 is fine. Now that we have our image, or you can actually read in an image. If you already have an image that looks like that, go ahead and imread your image. Okay, so that's absolutely fine. Now, how do we define our Fourier transform? It is DF. Let's call this DFT, and it's in OpenCV. It's called DFT, which stands for discrete Fourier transform, right? We are not dealing with continuous because our data is discrete. So in OpenCV, there is discrete Fourier transform. Go ahead and import it. And uh, if you look at the documentation of this discrete Fourier transform, it works only with float 32. So let's actually convert our uh, image into float 32 values. Okay, and you can actually define flags right here, and in this case our flag is going to be output a complex number. So I'm going to output a complex number. Again, there is a lot you can do. Go ahead and look at the documentation for discrete Fourier transform under OpenCV, but I'm just using the most common way that I always use when I do image processing. Okay, so here we are creating a variable called DFT, and this is nothing but a discrete Fourier transform of our image, which we converted from, I don't know, 8-bit integer to floating 32. Okay, so now if we run the code up to this point, you should see that my DFT is 256 by 256 float 32, and it has two channels. Okay, if I open this DFT actually has two channels. Okay, and don't pay attention to the numbers yet, but the two channels correspond to one being real, one being complex. Okay, our input image is only a gray image here, but our output has two channels, one corresponding to the real part, the other one corresponding to the imaginary part, because this is the complex value. Okay, so now what do we do with this? Okay, this is a complex value. We actually need to calculate the magnitude spectrum. Okay, again, this is the amplitude, and the magnitude spectrum is nothing but 20 logarithmic value of the magnitude of this whole thing. Okay, again, this is a math thing. You can read a lot about discrete Fourier transform, but for now, I'm just going to print out the magnitude spectrum. You don't need to do all of these, by the way, to use Fourier transform for image processing, whether you want to do high pass filtering or low pass filtering. Okay, just go ahead and use these, but it helps to understand exactly what's going on. Okay, so now it is 20 logarithmic, and how do you do log, and which is part of your numpy 20 log. Okay, and now we need to actually get the magnitude of this DFT. So, and there is the function inside within OpenCV, cv2.magnitude. Okay, if you have a complex number, you can actually use this. Okay, so the magnitude spectrum is nothing but 20 log of this magnitude. So I have this magnitude of what? Of our DFT, right? And let's actually look at the real part and imaginary part. Okay, so I'm going to take all my x pixels, all my y pixels, but then channel 0, which is our real part. Okay, and then DFT, and same thing, all of x, all of y, and then my imaginary numbers. This should do if I haven't made any syntax errors. Well, let's go ahead and run this just to confirm that, okay, everything is fine. Our magnitude spectrum is a float 32. Now let's go ahead and plot our magnitude spectrum. In fact, when I, okay, if you pay attention here, if you actually look at the execution here, it says runtime warning divide by 0 encountered in log. So if I actually plot this, plt.im show magnitude spectrum, if I actually plot this, it may look a bit weird because we may have a whole bunch of divide by zeros somewhere. And I wonder if that's where this is coming from. Let's run the whole thing one more time. Yeah, it's divide by 0 encountered. Anyway, what does that mean? Well, we are doing a logarithmic operation here, right? Now, if you have these value to be 0 somewhere, then log of 0 is indeterminate. I hope I'm making sense to you, life science people, especially you guys, if you don't have any background in this topic. Okay, so apparently some of these values turn out to be 0, so it's actually giving me, throwing an error in a way. So let's just add like a value of 1 to it. Okay, then hopefully it should be fine if I go ahead and run this. Okay, so at least you see that error is gone right now. Okay, and now why do I not see anything over here? Okay, in fact, I should have. Just a second, let me check my code. Let's actually change this to 30 and see if that looks the same even if I do that. Now, the thing is, uh, by default, it's actually using this top left corner as the center. Okay, so it's using, so we need to first, we need to move this to the center. Uh, Now, this is a very common operation that we do in especially in image processing, because there must be something going on over there, but then we want to move this to the center. Okay, and there is an operation for that in OpenCV. It's called FFT shift. Okay, it shifts this FFT from the top left corner to the center of the grid that we have over here. Okay, so let's go ahead and do that. Okay, so let me do that again. What we are trying to do is shift this DFT, which is nothing but we are rearranging this Fourier transform, right? By shifting our zero frequency from the corner to the center. That's all we are trying to do. Okay, and let me call this DFT shifted or just shift. Okay, and the way we do that is in NumPy. Again, I think even in OpenCV there is a way you can do that. FFT shift, and we are doing shifting our DFT. Okay, now because I did that, let's actually use our SFT shift here and also shift here. Magnitude spectrum, let's go ahead and plot it so we can actually see. Now you see the line, yeah, right there. Previously that was in the top left corner, which made it very difficult for us to see. So now the center, it actually moved it to the center, okay, right here. Let's do this again one more time when we import an actual image so it makes sense to you, okay? But for now, let's stick with this. Okay, so I think it's, in fact, let's actually plot all, let's actually plot both the image and the output at the same time. So for that, I have a piece of code right there. And let's see. So we are going to plot the image and we are going to plot our magnitude spectrum side by side. Let's go ahead and run it. Okay, so now pay attention to the frequency here in the input image, and it's very difficult. Probably if you squint you can see there is a peak right here, there's a peak right there. If I change my frequency, for example, let's go to a broader, smaller frequency right here, and run this code one more time. Now you can see these two dots got very close together. Now let's actually change this to the to the opposite side. You see the peak number 1 is right there. The peak number 2 is right here. These two over there. Okay. So this lesson number 1. is as the spatial frequency increases, which means when the bars get closer or the peaks get closer, the peaks in the DFT, okay, the peaks here, this one and this one, they're actually getting farther away. Yeah. So the higher the frequency, the farther these peaks are actually getting. In fact, if we rotate this image, let's go back to 60. Okay. No, this is fine. 3 is okay. What I wanted to do is, what is the easiest way to rotate? I wanted to rotate the image from vertical to horizontal. Um, uh, um, yeah, let's actually, I'm overthinking. Let me just rotate this. This may not be like the ideal way, but let's just rotate this by 90 degrees, okay? And IMG, okay? This should do the job. So if we run this, then okay, so there is your horizontal. You see the output of my FFT is now vertical right there. The spacing between these two did not change because the frequency did not change, but the orientation changed. Yeah, if I have an image with bars that are going in a horizontal way, 45 degrees, like from left to right, okay, then your FFT image will have a line that's going from top left to bottom right. Okay, so the FFT image reflects the information that you have in your input image. Now, in reality, you don't have just one sine wave, right? Your image is composed of many, many things, and that's exactly what FFT is going to reflect. So instead of all of this stuff, if we replace our image, okay, with something that we are used to, okay, what are we used to? We are used to our image equals to, let's say, where do we get cv2.imread, and let's actually read an image, images slash what do I have? Let me just give me a second so I can see. I mean, we can actually open any random image. In fact, let's actually open. I have an image called alloy.jpg. Okay, and we can actually open it in grayscale. Let's go ahead and run it. So here is the image on the left hand side. On the right hand side, you see how you have like this cluster in the middle. And by the way, the middle represents the low frequency. Okay, the corners represent the high frequency. If you do not do this DFT shift, okay, if you don't do that, okay, then it's the other way around. Again, I don't want to confuse you. In fact, let's actually, I just saw here that I have an image called 2D underscore sign.jpg. Okay, so let's actually look at this, and hopefully this will be what happened. I don't have a 2D sign.png, 2D underscore, oh, sorry, not JPEG, PNG. Okay. Okay. So this is, well, I guess I just got this as an input image. Sorry about that. Let me actually pick an Mona Lisa.jpg. Okay. I'm trying to find an image that makes some sense. Well, that's fine. Like, I kind of give up. But one thing I promised to show you is how the shift actually works. Let me comment that shift out, but we need a shift. I'm going to call this as DFT. Okay. So all I'm doing is I'm not shifting the image. I just want you to see how the DFT output looks like if we do not shift it. Okay. So it should look, you see how it looks exactly opposite of this image, where in the corners, okay, around the corners you have this low frequency component, and in the middle you have the high frequency component. Okay, now the reason again why we are doing this DFT shift is to make sure all these corner points come to the middle, making the low frequency accessible. So that's why we actually did that, okay, by shifting it, and the low frequency would be somewhere in the middle, and all high frequencies are out there. Now, if I want to build a high pass filter, I would just mask all the low frequency components down here, and then only let all the low frequency components out there. So that gives me, yeah, or I should say, all the high frequency components. And what are the high frequency components in images? These are the edges. Okay, so the edges are, if you want to do edge filtering or if you want to get edge detection, then just mask out the center and then let only the surrounding ones. If you do exactly the opposite, if you mask the surroundings and only let the center ones go through, then it would be exactly the opposite effect, right? So now it's almost like a smoothing filter. So the image, the noise would be smoothed and you have like a very nice, but then the edges would be blurred. Okay, so you can be a bit creative. You can actually create a mask that has a unique shape to let certain frequencies through. So these are all called band pass filters. Okay, so now you know, hopefully, how our original image can be represented, or the information in the original image can be represented in the Fourier space, okay, which are the frequency space. And in the frequency space, you can apply certain masks, certain operations, and then convert the image back to original. Okay, I'll cover this topic in the next tutorial. And then, I mean, this is one way of filtering, and this is called band pass filtering because you're letting certain bands through and filtering certain bands out. Okay, so this is exactly what Fourier transform is, or discrete Fourier transform is, and how it can be actually used for image processing. I hope it made sense to you guys, and I refrain from using a lot of math. In fact, we could have gone a bit deep into this exponential component and how e to the minus j, whatever that thing is, nothing but a combination of a sine component and a cos component and real and imaginary and all that stuff. But I just wanted to focus only to the image processing side, and I hope it made sense to you. So please stay tuned for the next tutorial where we actually extend this by creating a bandpass filter. Okay, thank you very much. Please subscribe to my channel and let's talk in the next tutorial.